So I just wanted to point that out. Our review. So let's see if there's nothing. Oh, yeah, we're going to turn it at the end. So I can just pick on Marlena. Marlena, calculate the pH of a strong acid solution. How would you go ahead and do that?
The negative log.
Negative log. Yeah, 0.23. No big deal. How about the next one, though, Jackie? We want to calculate the pH of 0.23 molar HCN. What would be the job to do that? We had a formula. We had, see if I can confuse you some more. We had a formula. Is that what we're supposed to do? Right? It's a weak acid. Naya, what do we do? Make an ice table of what reaction? Ka, right? Make a Ka reaction, do an ice table. You're going to have to be told, Desiree, what? In order to figure this out, you have to be told what for HCN? It's Ka or pKa, whatever. You have to be told the Ka. So yeah, exactly. Do a Ka reaction and then do ice. Okay. You'd have to be told it.
Oh.
Right? These are just how would you do problems.
Oh.
We've done so many of them, I don't think we need to sit down and do it. Right? What is the technical difference, Danielle, between 0.23 molar HCN and 0.23 F HCN? What's the difference? Gloriana, what's the difference? It's the same to me.
Yeah. Isn't it like they kept switching back and forth and me getting all mad about that?
Yeah.
Like, why can't they just keep it the same?
They should be consistent. They're not.
Concentration in all its form is formality.
Yes, exactly. The concentration in all its forms is the formality. So if I'm going to give you a problem like this, calculating, find the find the pH of a 0.23 molar HCN solution, I shouldn't be saying what? What's wrong with that sentence? What's technically wrong? Yeah, that should be a F. Because if it's molar, it technically means that in that ice expression, right? Oh, well, that's just HCN. H plus Cn minus. If it was this, technically what you're saying, technically what you're saying by writing molar is that this answer right down here is 0.23, right? That is the concentration at equilibrium is 0.23 molar. It's like in full systematic treatment, you find the concentration of all these different little species. That's all big M, because that concentration of that species is this. Okay, not in all of its forms. So we should be writing formalities. But once you get out of that chapter, they go back to their bad practices. How is the degree of dissociation of a weak acid found, Andy? How do you find the degree of dissociation of a weak acid? It's you're pretty much right, right? It's this. right? It's that alpha. You find alpha. F is the formality that you start out with of that weak acid. X is the X in ice. Exactly. Okay. Dissociation of water. Gloriana, what's the chemical equation? Just stop me anywhere along here if I lost you, if you're not sure about something. Gloriana, what's the chemical equation for the dissociation of water?
Isn't it 1 times 10 to the negative 14?
1 times 10 to the negative 14. That's not a chemical equation. What did you just name? What did she just name? Anybody? She named Kw. She named the equilibrium constant for the reaction that I asked for, right? Kelly, what is the chemical equation for the dissociation of water? And the hint is what Gloriana gave us. That's the equilibrium constant, but it's not much of a hint. Anybody?
Isn't it the concentration of hydrogen multiplied the concentration of OH?
That would be finishing the Kw expression,
Oh.
but that's still not a react.
Yeah, it's just H2O liquid with the equilibrium arrows gives you H+.
There it is.
Oh.
There's the chemical equation for the dissociation of water. Okay. And products over reactants, you're right, gives us the Kw expression. EXA, part A. I have 1.23 molar potassium hydroxide. Name every ion in this solution, regardless of its concentration. Then describe the source of each ion in the solution where it came from. Ida, you lucky person. What's every ion, every species present? What would you name? Now, K with a what, though? Plus, yeah, because there's a big difference. K, okay, keep going. OH. Any other ions? H plus? Does everybody agree? Because of the dissociation of water, right? Okay. There they are. There's our 3 ions. Now their source. Brandy, where does all the K plus come from? What's the source of the K plus? The KOH. Good. What's the source of the hydroxide, Monica?
Water.
Or no, the K. Yep, same thing.
The hydroxide is from the
KOH.
KOH. That's 1.23 molar, right? From the KOH. Where's the hydrogen ion from?
Water.
This dissociation of water, right? So, and you could argue,
Yeah, I said that has both KOH and water.
what's that?
That it comes from both KOH and water for the hydroxide.
The hydroxide, you could argue, comes from the KOH and water. However, that's such a dinky amount, right? Because the fraction of hydroxide that came from the dissociation of water, how could you calculate that? The fraction of, because you're right, the fraction of the hydroxide that came from the dissociation of water would be what over what? The amount of hydroxide that came from the dissociation of water is exactly equal to the H plus. So, because for every H plus that's created, and OH minus is created. So the fraction of hydroxide that's from the dissociation of water, just divide, right, The moles of H plus, or the concentration of H plus, or the concentration of OH minus? If they want percent, multiply it by 100. That's the game that we were playing a while back. Do you remember that? A little bit, maybe? Okay. At some point, there's a particular concentration range where we have to do a full systematic treatment. Now, this definitely isn't in it, right? You don't have to do full systematic treatment for this. If you want to find the pH, I suggest finding POH first, and then using pH plus POH is 14. So we don't have to do full systematic treatment for 1.23 molar KOH. But we do for what molarity to what molarity of KOH? Brandy, what molarity to what molarity? Very good. 10 to the negative 6 to 10 to the negative 8. 10 above and 10 below, neutral, where water's just sitting there pure. Okay. We have one EXB. Oh, Ricardo, we have EXB. They say what? That you have 1.23 molar sodium fluoride. Name every ion in this solution. Okay. Na plus, F minus. Yeah, it's not an ion. But let's list it anyway. Who cares? Well, let's not list. They didn't ask for ion. Let's won't list it. Na plus, F minus. And H plus and OH minus. Okay. I think this one, what I was driving at, do you see what I was probably driving at? Well, we can answer the question. The sodium, everybody, it's coming from the sodium fluoride. We probably should list the HF because name every species or something. Because otherwise, that's what the question is really driving at, right? Because right?
Are we going to have more systematic treatment of equilibrium problems in this test?
We're going to follow the homework.
We're going to follow homework? Okay.
If you had systematic treatment in the homework since the last test, well, it's very, very likely. Possible. I shouldn't say likely. It should be possible. Okay. So what is the source of the fluoride and the HF? The concentration of fluoride and the concentration of HF, those two had better sum up and add up to be what number? The concentration of fluoride and the concentration of HF?
1.23.
Better add up to be 1.23, right? Because fluoride in all its forms is going to be 1.23 molar. Okay, so that's kind of what I'm playing around with. I think this is the one that applied more so for what we were talking about. Because I remember when this started out, they asked, what's the fraction of hydrogen ion that's from the dissociation of water in this solution? So I remember that was asked in the homework. Out of all the buffers listed in the table, Desiree, out of all the buffers listed in the table, how is a buffer chosen for a particular application? How do you pick a buffer? By pKa. You want the pKa to match what? The pH you are interested in. Good. Okay. Why? She's right. Why, Marlena, are buffers chosen in that way? Now, it may not be perfect. You may not, if the pKa is 4.6 and your buffer's going to buffer at 4.5 is where you got to have the pH. So you pick this buffer with a pKa of 4.6. It may not match perfect, but it still works. But why are we picking them this way? You want to remember? Gloriana, you remember? Once the pH nails the pKa, what can you say about the populations in that solution? Populations of conjugate acid and conjugate base. What can you say about them? They are, well, that's always in equilibrium, but the populations are equal. There's substantial amounts of conjugate acid and conjugate base. It's right in the bloody middle of the population. Because you're always at equilibrium. You can adjust the pH and it goes back to equilibrium. You're always at equilibrium. But the idea here is you pick pH equal to pKa because then you have equal amounts of acid, and conjugate base. You can buffer either way, and because you don't know which way your buffers are going to need it. I mean, it's the whole idea of a buffer system. Okay, then we had some questions like this. Sabina, we had some questions like this. How do you prepare a buffer? Right now, and we're picking benzoic acid, and we want the pH to be 4. You want 250 mils of this stuff. What was the idea here? Oh, don't we need a concentration, don't we? Let's say 0.8 molar. How do you do this? No, that's going to be way too much. What was that, Ida?
Where you're adding the liquid to about 75 mils of water.
Oh, I see what you're saying. Okay, you're jumping ahead. So what Ida's saying is roughly around 200 mils of water, you're supposed to add so many grams, right? Why did she say 200 mils? She kind of jumped in the middle. I don't care what the number is. It's just the majority of the water. Why?
Leave space.
Leave space to adjust the pH. Exactly, to the pH you want. Now, what about this? To me, the very beginning is this part. How do you get that part? Kelly, how do you get that part, the grams? Yeah, from the molarity of the benzoic acid, you know the volumes, you can get the moles. Now, if you don't know what the molar mass is of benzoic acid, if you don't know its structure, you just have to find it in the table and figure out all the C's and H's and all that and figure out the molar mass, right? Make sense? So you can get the grams by using these two and knowing the structure. You need molar mass. So then you get the grams, you put it in the majority of the volume, like Ida was saying, and then Ricardo said, then adjust the pH with some acid and base, and you can make this question really ugly and complicated if you want. Like, just imagine the sentence is this being a paragraph this long and saying, you have 250 mils of 0.2 molar HCl and 88 mils of 0.1 molar NaOH. Those are only in there just so that you can adjust the pH. That's all you do is you just say adjust the pH until you get pH of 4, then dilute it up to the mark. You don't care how much you put in there of each. So, because the pH is just bouncing around. It's at equilibrium the whole time. You adjust the pH too high, too low, too high, too low, until you finally nail it at pH 4. Then once you get at pH 4, hopefully you're close to 250, so the pH won't change as you bring it up to the mark. That's why you added 200 mils in the first place. What is buffer capacity? And what is the expected range for a pH buffer? There's really two questions. Let's do buffer capacity first. Naya, what is buffer capacity? Buffer capacity. Like your blood has a buffer capacity. Coca-Cola has a buffer capacity. That means what? Yeah, you add, the buffer's trying to buffer the pH, you're adding some acid or base, and when you keep adding acid, it's got to quit sooner or later. It's going to stop working. Because if you keep adding acid, what's reacting in the buffer? The conjugate base. Conjugate bases react. Keep adding more acid. More conjugate base reacts. More acid. More conjugate base reacts. Well, it's going to end up gone sooner or later. Okay. So there's a general range for a buffer. You keep adding acid, and the conjugate base keeps reacting. And you're adding an acid, so the pH is dropping a little bit. Not as much as it should, because this acid reacted. But they say typically when you get down to what pH, your buffer capacity is gone. Without even doing any calculations. They're saying, look at your pH. You're not going to be able to buffer anymore. Your buffer system's reached its capacity. What was the general range? Plus or minus 1 pH unit from the what? Plus or minus 1 pH unit centered around what? pKa. Exactly, centered around the pKa. So if the pKa is 4.6, you keep adding acid, it keeps getting a little more acidic. Once you reach 3.6, they say your buffer capacity is shot. It's not going to buffer anymore. It's still working a little bit, but not very well. How about this one? Brandy, more concentrated buffer solutions have a greater buffer capacity. And why, Andy? Simply because
There's more reaction.
yeah, there's more conjugate acid and more conjugate base. There's just more of it. So you can definitely buffer better. Circle the names of all the buffers that exist as the conjugate base. So we'll just start at the top and go down, and you either say circle or don't circle. Okay? So we'll start in the back with Kelly, and we'll just go around. So we want to circle the ones that are a conjugate base when put in water. So, and here's all of our names. So we're going to circle these names. So we're going to put benzoic acid in water. If it acts as a conjugate base, we're supposed to circle the name. So would benzoic acid act as a conjugate base? Yes? Everybody agree? When you've done this a bunch of times, like I have, there's some easy way. There's some easy answers. Whenever the name has acid in it, it's going to be an acid. So you don't even have to look at the structure. You know, I never trust myself, but now I finally got to the point where, okay, fine, I don't even have to look. I trust it. The name's acid. I don't have to look. But I look anyway. There's no plus on it. If there's no plus on it, that is the neutral form. So don't circle this one. That's conjugate acid. Okay, Brandy, you're next. Do we circle? You have a solution of benzylamine.
Yes.
Yes. Andy, you have a solution of 2,2' bipyridine. Yes.
Oh, so we're looking at the name.
Circle the names of all the buffers that exist as A- when put in water.
Yeah, I thought we were looking
Okay.
at the structure.
You need to look at the structure too to figure this out. Okay, and who am I picking on? Monica, you have a solution of boric acid. Trust it. Trust it. You have a solution of boric acid. What we are doing is we're preparing ourselves for this stuff. That's what we're doing. We're preparing ourselves here. Oh, are you going to have to add KOH? Or are you going to have to add HCl? That's what we're preparing ourselves for. So if you have a solution of boric acid, it's going to behave as an acid. So you're going to have to add a base. All this question is saying circle all the ones that are acting as a conjugate base. So we don't circle it, right? Okay, so don't circle it. Gloriana, you have a solution of bromoacetic acid.
No.
Don't circle it, yeah. Mel, dimethylgloxime. Yeah, don't circle it. That's definitely behaving as a conjugate acid. Butanoic acid, Ricardo.
That one, talking
Yeah, don't circle it. We're at maleic acid, Jackie. Maleic acid. You have a solution of maleic acid. I lost it. Here it is. Solution of maleic acid.
No.
Don't circle it. You have a solution, Desiree, of fumaric acid. Now it's acting as a conjugate acid. You have a solution of butylamine. Yes. Very good. Okay. Whoop. Circle an A. So if it's circled, they're going to react with H plus to adjust the pH. Would dissolved cyclohexylamine, Danielle, react with NaOH or HCl when put in water? Dissolved cyclohexylamine. React with HCl. Does everybody agree? Everybody agree? Okay.
I told you I give up. Can you hear me?
Don't give up.
I don't know.
Don't give up. Okay. So again, it starts over here. So these are all these structures, Danielle, in these tables are all, every single one, are all HA or are they all A minus? Every single one of these structures is HA or A minus. That's probably where your confusion is starting. Every single structure is what? Look at the big blue H. And every single structure has a big blue H. Every single structure corresponds to H. Say it. What's a conjugate acid? We don't say H is a conjugate acid. What's a conjugate acid? What's the structure of the conjugate acid? What are you even saying? H. Finish it. HA. Well, say it with confidence. HA. HA. These are all the big blue H's. Okay. The problem is, if you see a plus on there, that's not how it exists in, that's not how it's going to exist in the bottle. It can't. It can only be a neutral compound. So you look at this HA, and there's a plus on it. Problem. You got to remove it. The name is going to correspond to this thing with a H lost. So that makes it a conjugate. That makes this a conjugate base, right? This name is the conjugate base, A minus. A minus can only react with H plus and make this thing. So this has to react with HCl. Okay. If I wanted to, now this is where you can really, you really understand this, I think. I want to change this answer to NaOH. How do I, and I want to use the same buffer system. How do I change the question? I want the answer to be NaOH, but I want to use the same buffer system. So this is what I have to have in the bottle. How can I get this in the bottle? Make a, starts with an S. Make a salt. Make a salt. Have a cation and an anion. Great cation. There it is. Okay, there's my cation. Now I just got to stick it with any anion I want, but the anion can't mess with the pH. So that really narrows down the anions you can use. It really does. It can only be anions of what acids? Strong acids. Those are the only anions you can use. Otherwise, man, you're going to have a complicated problem on your hands. Forget about just writing one Henderson-Hasselbalch equation. You have to write two of them. And then you probably have to do with some systematic treatment because things are interacting with one another. And these equations are dependent on one another. So any anion you want, but make it a conjugate. Make it the anion of a strong acid. What are those? Chloride, iodide, bromide, not fluoride. Sulfate. Now sulfate won't work though because it grabs one H, all of a sudden it's a conjugate it's a weak acid. So sulfate won't work. Nitrate's a good one. And perchlorate. There's really only 5 that it could be. Okay. Okay. Make a salt. Make it a salt. So okay, so we didn't finish the question. So how would you name this? Cyclohexylamine nitrate. Now my answer will be NaOH. Okay. That's how I write these tests. Okay.
Our table will be in color, right?
The table, it'll be just like if you printed out this, that's what it's going to look like. Because I can't get it in color. But the H's will be boldened.
Oh, okay.
Right?
Because on some of these, it's kind of, I don't know, it's a little bit hard for me to tell.
But if you have trouble reading the table, just ask. I can be glad to help you out.
And then I thought the pKa would help out, but that didn't help for anything because butane 2,3-dione dioxide, it has a high pKa, but it's still an acid.
No, you can't go by pKa at all. Okay. So now we're into questions that we've just done. Okay. This is like the homework. This is just like the quiz questions, right? This one's different though. You should do this one. Write the Ka and Kb reactions, and then we'll take our quiz. Go ahead and write the Ka and Kb reactions for the maleic acid buffer system. Where's maleic acid? We don't have it, so let's change it to propanoic is right there. So let's change it to propanoic. Write the Ka and Kb reactions for the propanoic acid buffer system using the correct chemical formula. Write the Ka reaction and the Kb reaction. See the trick? Pretty much just identify the conjugate acid, write a Ka reaction. Identify the conjugate base, write a Kb reaction. Is all it's really asking you to do. So your Ka reaction would look something like this, hopefully. And your Kb reaction should be this guy, right? This compound plus H2O gives propanoic acid plus hydroxide, right? Would be your Kb reaction. So. Alrighty then. Now the fun really begins, where the meat meets the street. Yes, and you end up with the conjugate acid again. Perfect. Okay. So this is a good example, right? This is what it's going to look like on the exam. It has to look like this, right? If you can read the table here, you can read the table on the exam because it'll be the same thing. Oh, I haven't thought about that. Naya's asking, are we going to have a review on Monday? We went through pretty much everything. It's just these problems that are left. Would you guys show up for that? I mean, you already...
Yeah, we'll do a pizza party on Monday and review. That sounds great, man.
Is anyone going to show up? Who's going to show up on Monday at 12? Has to be like 12:30 because I have class at 11. At 12:30 to do this kind of stuff. Just raise your hand so I know how many. 1, 2, 3, 4, 5, 6, 7. Okay.
Sounds it takes to get it over.
Then no pizza for you. I'm trying to say it like that soup guy, the soup Nazi.
Instead of pizza, we'll get cafeteria food this time.
All on me. I got the money.
She gets soup. So then I can be like the soup Nazi. You don't watch You never watch Seinfeld? Yeah, the soup Nazi. Yeah. Yeah, you gotta watch Seinfeld.